Hi everyone. Well, happy Monday. I mean, it's I know it's Monday for you. It's not Monday for me, which is why I'm wearing my Norwich City tie today as a Friday one. It has all got too confusing the way I was doing it before, and I just want to make sure that hopefully Norwich still have at least a 7-point gap at the top of the championship table by the time you're listening to me, as they do now as I'm talking to you. Anyway, before we get on with the main part of the lesson, today's starter is called a futoshiki, which is a little puzzle all hinging around inequalities, which is an essential maths skill. I'm going to show you how it works and put in one number for you now and challenge you to see if you can, before the next lesson when I will show you the final solution, see if you can work out where to put all the other numbers. It's quite tricky, but quite fun. When I say fun, you may think, really not sure that I agree with your idea of fun, and philosophers have argued over different types of fun. There are types of fun which are instantly rewarding and others that take a little longer. Anyway, here's the puzzle. So an inequality is telling you whether one number is bigger than or smaller than another. So it's like an equals sign, except that it's been pinched at one side to say that it's not equal, and more than that, the number, whatever you've got at the shorter end, the pinched end, if you like, is a smaller number than what you've got somewhere else. Now the numbers 1 to 5 are going in every row and every column, but in a mixed up order, and also wherever you get an inequality, it's got to obey that rule. So this cannot be a 1, it cannot be a 2 because we've already got a 2 in this row. So it has to be a 3, a 4 or a 5. Down here, this means that this must be a 3 or a 1. It cannot be a 2 because we've got a 2 up there. Now the number I'm going to place for you is going to be a 5, and the reason for that is, in this column I know that this number here must be smaller than 4, so it's a 3 or a 1, and this number here must be smaller than this one. Now we don't know what this number is, but the biggest number it could be is a 5, meaning this number can only be, well, it can't be a 4 because you've got a 4 there, so this number is a 3 or a 1 because we've got a 2 up there as well. So that cannot be a 5, that cannot be a 5, there has to be a 5 in each column, so I'm going to put a 5 there. And what I would like you to do is make a copy of it. If you can't, you don't have to use a a printer or whatever. If you've got some square paper, you could do what I've done there to show you exactly what I would do there, and you can set it out exactly the same. Anyway, you don't have to do it now, you don't have to do it at all, but if at some point during the day you get really bored and think, well, what shall I do? I'll have a cup of tea and just mull over a puzzle, you may find you actually sort of quite enjoy it. Now, strangely, the recording I made for question 1 has somehow vanished, so I'm going to go through it again, first time for you, but I've done the working already, so I'd like you to look at the question, write it down, and see if you can write a probability tree diagram for it, and can you work out the probability that Tina takes 2 blue counters. Right, pause the video and have a go. Here comes my working. So what we've got is, from bag A, she's got 5 reds and 3 blues. So it's 5/8 for red and 3 out of 8 for blue. For bag B, she's got 4 out of 9 and 5 out of 9. And it doesn't make any difference. It's independent probability because it doesn't matter what happens to A, it'll be the same for B. So bag B is the same in both instances. And then I have gone through and I've worked out all of the probabilities here for along the branch. The chance of 2 reds is 5/8 times 4/9 is 20/72. The question I asked you, and is asked down here if you've already got it from the worksheet, is 2 blues, which is 3/8 times 5/9, which is 15/72. But the reason I went through and did all of this was I wanted to make it clear that whenever you've got probability tree diagrams, if you work out all the things that can happen and then add them up, they should all add up to 1. In fact, at any stage in the tree, those two branches add up to 1. Those two branches there add up to 1. Those two add up to 1. But then when you've multiplied everything that can happen right from the beginning through, the 4 things we've got there should add up to 1, which is 72 out of 72. And they do. Okay. Pause the video and have a crack at number 2. You can use a calculator. These virtually always come up on a calculator exam, but test yourself as well in terms of your mental thing. Do both if you can. If you can, of course you can. If you can be bothered, I suppose I should say. Right, chess. 0.6 chance that Hannah wins. That must mean that there's a 0.4 chance she doesn't win. Chess and bat, it doesn't make any difference apparently whether she's just won the chess, although in reality it probably would, because it would make you feel a little bit more confident, wouldn't it? Probability of winning backgammon is 0.7, so 0.7 plus 0.3 makes a whole. And if you've decided to turn this into tenths and do it as a fraction, then that's absolutely fine. The probability that Hannah will win both games, well, that's that one and that one. So it's 0.6 times 0.7. I'm not going to go through all the different ones that I did on the last one. If you want to, you can. They should all add up to 1. Gives you 0.42. And that is question 2. Moving on to question 3. Pause the video. Give it a go. Right then, so you should have 4/10 and 6/10, and then on the bag, make sure you're careful though. You can see I started to make a bit of an error. So second bag, we've got 3 reds and we've got 8 balls altogether in that bag. So then it's 5/8 there, 3/8 and 5/8. And we just want the probability that green takes 2 green balls. I think it means Rachel takes 2 green balls, but there you go. So green and green is what we're talking about. 6/10 times 5/8. 6 5s are 30. 10/8 are 80. If you've got any equivalent fraction to 30 over 80, like 3/8, then that's fine too. Another very similar one here. So rip through this as quick as you can, but taking care, don't over rush. And you should have got Joe winning tennis is 4/5, so losing is 1/5. Winning squash is 7/10. Losing will be 3/10, or not winning 7/10. And because of course she could draw, couldn't she? So just not winning. 2 things that can happen. So now that we've got that, we want the probability she wins both matches. So that's that one and that one. So and means we multiply 4/5 times 7/10. 4 7s are 28, 5 10s are 50. 28 out of 50. If you wanted to leave it as 14 over 25, you're allowed to. If you went for 56%, that would be okay. But 28 out of 50, why do more work than you need to? Now then, this question gets a little more interesting, so take your time, write it down and go for it. So each day Paul wears either a black tie or a red tie, and you assume, as we have been doing for all of these, that it doesn't change. If he had wore a black tie on a Monday, it's not going to change his mind. Now you may think that's not true. If he had a black tie, then for some of us that would mean I've got that tie lying around. I'm probably more likely to put it on the next day. For others, maybe they think it's more likely that they'd have a change. But there you go. So you've got 5/9 and 4/9. Why it's that probability, I do not know. Maybe he's got 5 black ties and 4 red ties, and he keeps them in a box and he takes them out at random without looking or something. Who knows? Anyway, we want the probability he wears different coloured ties. So that could be black tie on Monday followed by red tie on Tuesday. Or it could be red tie on Monday and black tie on Tuesday. Tick. What it cannot be is 2 black ties, and it cannot be 2 red ties. So we get into an and or situation. When it's or, you add. So this is one solution, or this solution. They both work. So first of all, black, then red is going to be 5/9 times 4/9 is 20 out of 81. So there are 81 different ways, if you imagine that they were 9 different ties, that this could happen. 81 different ways that he could combine his ties. There are 20 different ways in which it could be a black one followed by a red one. And then we need to calculate the chance that it's a red followed by a black. And it's actually the same chance, but the other way round. So 9 times 9 is 81, 4 times 5 is 20, but there are 20 ways he could get a red one before the black one. And altogether that means that there's 40 ways it could happen. So then it's that or that, and that means that we add. So when we add fractions, the denominator stays the same because we've only got 81 different ways they could happen altogether. That hasn't changed, but the number of them that we're considering has. So we add them together in that situation, and we get 40 out of 81. If you've chosen to add at the wrong time, you may end up with an answer that's bigger than 1, and that's a real sign that something's gone wrong, isn't it? So do remember always at the end of any question to think, is that plausible? And that looks pretty plausible to me, and that's because it's right. So I have a butcher's at question 6, and see what you can do. You've got 3 options this time. You've got win, drawing and losing. 0.5, 0.3, it doesn't say the lose, and our task is to work out the probability that John wins both games. So you don't really need the information above now. You know you've got a win, a draw or a loss. Pause the video, give it a go. The chance he wins both games, so it's a win and a win, isn't it? So it's 0.2 there. Completing the probability tree diagram gets us 2 marks. So if we only had to do this, it would be much quicker, but we do need to fill all of these in. It doesn't say that the chance of him winning, drawing or losing the second game is affected by the first, so you assume it isn't. And that's because we're doing independent probability. So that gets you 2 marks, just filling that in. And that's 0.2 because 0.5, 0.3 and 0.2 adds up to 1. Right, the probability he wins both games. It's this followed by this. 0.5 multiplied by 0.5, or a half times a half, which is a quarter. So if you've got 0.25 or a quarter, you've got the right answer. Right, today's final question then is a little bit more intriguing. Bradley gets the bus on Saturday and Sunday. The probability he's late on any day is 0.2. You get 2 marks for filling out the probability tree diagram. And then they want the probability that Bradley's bus is late on at least one of these days. So pause the video and see how you get on with that. So if he's late on any day, it's 0.2. So not being late is on time or early, isn't it? So don't worry about that. It's just not late. 0.2, 0.8, 0.2, 0.8. Now, we want the probability that it's late on at least one of these days. There's a quick way and a longer way to do it. At least one of these days. Well, being late twice would be at least one of them, and just being late once would be at least one. So we want this one and this one and this one. So we can do it by saying 0.2 times 0.2 equals 0.04. You can do it by saying 0.2 times 0.8 is 0.16. 0.8 times 0.2 is also 0.16. And then you could say that the probability he's late on at least one of the days is 0.04, add 0.16, add 0.16. 6 add 4 is 10, add 6 is 16, so that gets us 0.36, and that is the right answer. But there is a quicker way you can do it. The probability that something happens, let's call that x. The probability that x happens is also equal to 1 minus the probability that x doesn't happen, which is what that little dash means. So if you think about it, if all of these are going to add up to 1, this must be 0.64, because 0.64 plus the 0.36 makes 1, and that is what you get when you do 0.8 times 0.8. So you could have saved yourself a little bit of calculation, and some of you may have done this by thinking, yeah, not and not gets us 0.64. That's the chance that it's not late at all, and then if I do 1 take 0.64, that gives me 0.36. And as Forrest Gump would say, that's all I've got to say about that. And I will, if you've never seen Forrest Gump, do see it, it's a classic. We will hook up again next time for conditional probability, when things get a little bit more interesting, because generally things aren't all independent, are they? If you're just rolling a dice or something, yeah, it's independent. But if we do something once, it affects our ability to do it again, doesn't it? So we'll have a little look at conditional probability tomorrow. Right, this is going to be the first of a couple of lessons on probability. The first one is just basic probability trees. I say basic, but it is seen as quite high level stuff, but generally we've got a pretty good record here at Ilfracombe of doing well on them, so have a good go at it. You can do this stuff, folks, and tomorrow or next time we will be going on to some conditional probability, which is a little more thinking, but just all good fun, really. Right, so pause the video, have a little go at this. What can you do? So there's 5 red counters and 3 blue counters in bag A. So in bag A, you've got a 5 in 8 chance of getting a red counter, and you've got a 3 in blue. Then you go to bag B, and you've got a 4 in 9 chance of getting a red one, and a 5 in 9 for blue. And that'll be the same again. It doesn't matter what happened in bag A, does it, to what will happen in bag B. That's what's known as independent probability, as opposed to conditional. Right, so that's the probability. That's 2 marks for that. I think this is one of the easiest ways to pick up marks in the higher paper, so make sure you always get those right. Work out the probability that Tina takes 2 blue counters. So if you add the 2 branches, they always add up to 1. You've got 8 eighths there, haven't you? You've got 9 ninths there. If you want to know the chance of this happening and then this, that's and in probability world means multiply. Now I'm actually going to do all 4 of these just for the sake of it this time. Red and red would be 5 eighths times 4 ninths. I say just for the sake of it, there's actually a good reason. Is 20, 8 nines are 72. Do not simplify them, the reason will become clear. Red and then blue will be 5 eighths times 5 ninths, which is 25 over 72. Blue and then red will be 3 over 8 times 4 over 9, which is 12 over 72. And blue will be 3 over 8 times 5 over 9, which is 15 over 72. Now the reason I've done this is because if you add all of these probabilities up, you want to keep it over 72, because that allows you to, because the denominator will be the same. 20 plus 25 is 45, plus 12 is 57, plus 15 is 72. If you've done it right, it'll all add up to one whole at the end. 72 over 72 is a whole. So work out the probability Tina takes 2 counters. That's this. I've done that working for you already. 3/8 times 5/9 is 15/72. Writing that calculation will get you 1 mark. Having that will get you another.